All right, so back to differentiability. We were looking at this yesterday. So differentiability means take the derivative ability. So we want to be able to identify where functions are differentiable and where they are not differentiable. So there are fundamentally three kinds of places where functions fail to be differentiable, where derivatives do not exist. Discontinuities. Any discontinuity in the function kills the derivative because differentiability implies continuity, right? But not the converse. If a function is differentiable, it must be continuous. However, continuous functions aren't all differentiable, as we'll see. Sharp corners, points where the function is continuous, but the derivative from the left is not equal to the derivative from the right. Okay, so there's a sudden change in the slope of tangent lines. Okay, and vertical tangents, of course, would never, because that's where slope is undefined. So the derivative can't be undefined there because the derivative outputs slope, right? Okay, so and then cusps. Well, we'll see when we see cusps. We'll talk about them. They're just vertical tangents that look like really sharp corners. Okay, infinitely sharp corners. Okay, so let's look at a couple examples of this. So are these functions differentiable at x equals 0? What about the one on the left? The greatest integer function. Is that differentiable at x equals 0? Does it violate any rules we just said? It's not continuous, so it's automatically disqualified, right? Because differentiability implies or needs continuity, right? Okay, how about this one? Well, same thing, right? At 0, this piecewise function is discontinuous, so it's not differentiable. Now, you could conceivably have, like, what if, and this is a question that sometimes comes up, what if this red line did this instead? So the slopes from the left and the right are both 0, right? But because it's discontinuous, the derivative does not exist. Okay. All right. Sharp corner. So we know the derivative doesn't exist there, right? Here's how we can sort of defend that, show why that's the way it is. So if we rewrite f of x as a piecewise function, what you guys tell me real quick, this is good review. What is the absolute value of x as a piecewise function? So we got to define parts of the domain. So on the domain where x is, you tell me, like where x is less than 0, let's do that one down here. Where x is less than 0, so x is negative, what is the absolute value of x equal to? Negative x. Good, because it has to multiply the input by -1 to make it positive. Okay, so when x is greater than 0, the absolute value of x equals x. And when x equals 0, the absolute value of x equals 0. Okay? All right, so then we've got this as a piecewise function. We could just differentiate this piece by piece. We could differentiate each piece of this piecewise function. Now, let's not go through the hassle here of having to do all the limit stuff. Let's just use the graph. Just based on the graph, can you tell me what should the slopes be when x is greater than 0 and when x is less than 0? So in the domain where x is greater than 0, that's the leg of the absolute value function to the right of the y-axis. What's the slope everywhere? 1. Okay, so the derivative is equal to 1, right? What's the slope of everywhere to the left of the y-axis when x is negative? -1. Okay, so what about at 0? Well, which one would it be? Do you see why it can't be either one of those? Right? There's a couple arguments for this, but go ahead. Yeah, you can't even have a tangent line there, can you? Because a tangent line depends on the behavior of its neighbors. right? In order to be tangent, it has to, when I zoom out, it should mimic the slope of the curve as the curvature disappears. Well, there is no curvature there. That's a sharp corner, right? So you can kind of finesse your way through that right away, saying, okay, that doesn't make sense. It doesn't even make sense to have a tangent line. But even if it did, here's a pretty elegant argument for this one. For the function to have a slope at 0, the only ones that would make any sense at all would be +1 or -1, right? Because at least in those cases, the ant, if he takes a small step to the right, he would experience a slope of +1. If he takes a small slope to the left, he would experience a slope of -1, right? So based on the relationship with a nearest neighbor, one of those would have to be the case. But which one would you pick? There should be no preference, right? This mathematical space is completely isotropic. It doesn't matter. There's no preferred direction anywhere. We can't assign a preference to right or left, right? We have perfect symmetry in this function, so we can't do it, right? Therefore, you can't define a derivative, because to do so would be to assign preferential status to one leg or the other, which clearly you can't do for a function, right? So it doesn't exist. Okay, so there is no derivative there. Okay, and again, our justification for that moving forward is just that it's a sharp corner. The derivative from the left is not equal to the derivative from the right. Okay, how about this one? Does the derivative exist? No. I'm going to get different derivatives from different directions. If I went through the exercise of calculating these derivatives, and I'm not going to do that. You guys are, you're practicing using your limit definition. You could all do that. But if I took this derivative, here's what I'd get. When x is less than 0, the derivative of -4x, well, that's just got a slope of -4, doesn't it? Right? When x is greater than 0, it turns out that the answer is just going to be 2x. Okay, but I can't, when we take a limit of the derivative as x approaches 0, look what happens. The limit of f prime of x as x approaches 0 from the left is -4, right? Okay, the limit of f prime of x as x approaches 0 from the right would be what? If I take the limit of, there's f prime of x. If I take the limit of 2x as x approaches 0, what do I get? 0. Well, those are not in agreement, right? Do you see why we're taking a limit there? Right? Because we want to know what is the derivative as we approach 0 from both sides. That calls for a limit, doesn't it? Right? Because those are not equal, the limit can't exist at 0. It has to make a sudden change, which is not allowed. Okay, you have to recognize on this one what this limit means, right? You just have to interpret that limit. Well, what is that? That looks like the limit of a difference quotient, right? So it's a derivative. It's the derivative, but what does the 3 mean there? At 3, yeah, when x equals 3, right? The 3 is what has been substituted for the x. So we're evaluating this derivative at 3. So this is really just equal to f prime of 3. Well, and at 3, we're just on that line. Just look at the slope of the line, and that's it, right? Slope is negative. It rises by -4, runs by 6, so -2/3. Okay? All right. So first of all, we're just going to check these things out one at a time, right? Does the limit exist as x approaches 5? Thumbs up or down? It does, right? Because the only place as we approach 5 we're on the, from either direction, we're on the top row of that piecewise function. The bottom row is the value that's assigned at 5, but the limit doesn't care what happens at 5. It only cares about what happens as you approach 5, right? So for part 1, if we take the limit of f of x as x approaches 5 is equal to the limit of x squared minus 25 over x minus 5 as x approaches 5. That's indeterminate, right? But how do I resolve that? Okay, I mean factor, right? Factor the top. That's just a difference of squares. So we get the limit of x minus 5 times x plus 5 over x minus 5 as x approaches 5. We cancel the offending factors, right, that are causing the indeterminacy. We let x go to 5, and then we just get 10 as a result. Okay, so the limit does exist, yes. Is the function continuous? No, because the limit approaches 10, but the value of the function is 5, right? So that means that this point has been displaced from the function. Okay, give me thumbs on that. Does that all make sense? Okay. Is the function differentiable? Do we even have to try? No, how come? Because it's not continuous. Differentiability implies continuity. In other words, differentiability requires continuity. So it's only one. Okay, good. Okay, so yeah, how does this work? Well, we're looking for the slope of the red graph gives us the value of the purple velocity graph, right? So what do we notice here? If we draw tangent lines, and that's really a good idea here, is to draw little tangents. Well, look at this tangent right here. That's zero slope, right? It's getting steeper. It's getting steeper. Maximum value right there. So there's that part of the velocity graph then, right? Starts with a value of 0, increases to some positive amount, and it actually looks like that amount is 1. It is 1. You can see if I look at the slope of this line, I rise by 5 and run by 5, right? Little squares, okay? Rise by 1 and run by 1, okay? Really what that means. And then once we get to here, it just stays at a constant velocity, which is what is shown there, okay? So there's the velocity graph. Now the acceleration graph. To be totally correct, you really need to have open endpoints there. How come? How come, Max? Because it's undefined, right? Because you have a sharp corner and derivatives are undefined at sharp corners. And so I need to omit that value from the domain of the acceleration function. Acceleration is undefined at 5, okay? And you see why, because think about what we're saying would happen there. We're saying you would instantaneously change your velocity from 1 to 0. Well, for any object with mass, that would require an infinite amount of energy to accomplish, which isn't available, right? Because if you, not many people are in physics here, but that would mean you're changing your momentum instantly, which you can't do. Rate of change of momentum is force, and that would require infinite force, okay? But we don't need to get too far into that. You just need to see that based on the shape of the graph, it's undefined because it's a sharp corner. Okay, give me thumbs on that, on the explanation. Is that making sense, what we did? Okay, and this stuff just takes practice. You get some practice on the homework on this too. Oh, acceleration. Okay, I guess I didn't talk about how we did that. Acceleration is the derivative of velocity, right? And so this first section of the velocity graph has a constant positive slope, right? So the acceleration is positive and constant, and then it shifts to a constant 0 slope. So the acceleration drops to a value of 0. Okay, does that help? I forgot to say that part. Okay. All right. All right. So why? Why would it have at least 2 zeros? Well, here's why. Look, if we know that the function is differentiable on the open interval from -2 to 8, if it's differentiable, what does that say about its continuity? It's continuous, right? Differentiability implies continuity. And if a function is continuous on an interval, on a closed interval, right, what does the intermediate value theorem tell us here? If we know that if f of 0 is 3 and f of 2 is -3, and it's continuous on the interval from 0 to 2, which it is, right? Because that's a subinterval of this larger interval where we already know it's continuous. Then the intermediate value theorem says that it has to pass through every intermediate value, including 0, at least once somewhere, right? So we know it has to have at least one 0 between x equals 0 and x equals 2. Agreed? By IVT. Okay. Also, if we know that f of 2 is -3 and f of 7 is +3, then it must also pass through 0 between x equals 2 and x equals 7. So you get a total of at least two zeros, at least, could be more, but we have at least 2 by IVT. Okay. And then, well, 2 is given, right? If it's continuous on the open interval from -2 to 8, then that means the closed interval from -1 to 7 is a subinterval of that larger interval. So that has to be true. Okay. And then how about this last one? For some c between 0 and 7, f of c equals -2. Well, let's see, between 0 and 7. So well, if you just look at between 0 and 7, it says 3 and 3. So that doesn't guarantee anything, right? However, we know that at 2, the value of the function is -3. So we know that between 2 and 7, the function has to pass through the intermediate value of -2. So therefore, if it happens between 2 and 7, it necessarily has to happen between 0 and 7, right? Okay, give me thumbs. Does that make sense? Okay, all right.